Okay, welcome to Stat 310 Lecture 8. So today we're continuing on in our new chapter, Chapter 8. And in particular, we're continuing on with the concept of sampling distributions, which is in 8.3. And remember that the overall goal in Chapter 8 is to develop a pretty general framework for using the data to estimate population parameters. And so we're going to first see how the plug-in principle for the sampling distribution leads to estimation procedure. And then we're going to go into our first kind of major general estimation procedure, which is the method of moments estimation procedure. And that's in 8.4. So recall, so just recapping what we covered kind of in the back half of the previous lecture. So recall that for discrete random variables, we have this notion of a sample PMF or probability mass function. And so that's kind of just the proportions of different random variable values within the sample. So you just add up when the random variables equal a particular value and then just take an average. So we saw a Netflix example, which we'll return to later, where we calculated that sample PMF. And so the key property that we saw from the previous lecture was that the sample PMF in expectation is the same as in expectation equals the population PMF. And once again, I want to emphasize the importance of this notation and understanding the distinction between the sample and the population. So the p hat x of k is the sample PMF. That's a function of the data, so what you see in the sample data. On the other hand, the population PMF, px of k, is a function of the population. So that's typically something you don't know, and you want to estimate that or determine some aspect of that from the data. And so the question is, how do we use this sample PMF to estimate our parameter or parameters theta? And so the general principle, which is this plug-in principle, is that to find an estimate for theta, which we're going to call theta hat. Once again, theta hat means that it's a function of the data. We're going to use the relationship between theta and px of k. These are population quantities that you can relate to each other. And then we're going to use that relationship to determine theta hat from px of k. So kind of just a simple diagram. If there is some functional that you can find theta from px of k, and we'll see an example shortly, then you just apply that same functional to find with theta hat from p hat x of k, and that gives you a perfectly reasonable estimator. So now let's return to an example that we saw in the previous lecture, which is x's Poisson lambda random variable. So we want to find an estimate for lambda. So recall that for the Poisson distribution, px of k is lambda to the k e to the negative lambda to the k, and this is for k equals 0, 1, 2, so for all non-negative integers. And how does lambda relate to px of k? So, what you potentially hopefully know or remember is that we know that lambda is actually equal to e of x. So we can kind of write that as and so that okay. And so so this is kind of the relationship, this functional h that you can use to go from the probability mass function. This is the population probability mass function to the parameter of interest, which is lambda. So now, what all that means is that lambda hat equals to, we're going to apply that same functional, but we're going to replace px of k with p hat x of k. P hat x of k. And so this is the plug-in principle. Okay, so you can clearly see that this is a perfectly reasonable estimate. And so we can, we can use the fact that, we're trying to calculate a population mean. We're trying to estimate a population mean, and so we're going to kind of use the sample PMF. to do that. And all we've done is plugged in the p hat x wherever we see px. So the idea is that wherever we see px of k in population, functional, we replace or plug in with p hat x of k. Okay, and that's exactly what we do here. So what do we get when we do that? So the definition of p hat x of k is okay, so this is by definition what we get for our p hat x of k. So this is the definition of and we can swap the sums as we usually do. There's a few conditions that we need here, but you can check that they would be satisfied. And something pretty cool happens here that if you think about the sum of k equals 0 to infinity k times indicator x equals k, that is essentially just going to be equal to xi, because, if xi equals k, then k equals xi, obviously, and you're summing over all the different possibilities, right? So if xi is 1 and you sum over like 2 to infinity, that's always going to be 0, and you're going to just collect the terms that give you the thing. So this is something to just work through in your own mind, but you can hopefully see that just equals to that equals to xi. And so what you end up with is that this is xi, which is just exactly x bar. So you have something that's, again, probably something that you could have guessed, that using the sample mean to estimate the population means generally not a bad idea. And we've shown that the plug-in principle gives you exactly that. So x bar is this is the sample mean, and lambda population mean. So and so so the plug-in principle suggests that that x bar is reasonable for lambda. We can certainly make this more general beyond the Poisson distribution. So in general, if mu is equal to e of x, and so px of k is the PMF, so that's just by definition equal to the sum over the range of x. Then you can say that by the plug-in principle, you can see that we're going to get that mu hat is just k times p hat x of k. And doing a pretty similar calculation to what we did before, this is just okay, and then this gives you xi. And so you get exactly that equals x bar. So we can see that the plug-in principle kind of gives you that mu hat equals x bar. And we can also think about the variance. So okay, and so if we wanted to estimate sigma hat squared, then we can again use the plug-in principle. And we have to replace the mu with mu hat because that is something we also have to calculate from the data, and this is by plug-in principle. Okay, and so So once again, I'm just, we're going to go through this calculation to see what we get. Do we end up getting the typical sample variance or something very similar to that? Okay, so now if we split this calculation up, we can see that you can expand out the square as you typically would. Okay, and so okay, and so you can see that when you do this sum of k in Rx, you're again going to get that using the standard properties of the indicator and the fact that we're kind of summing over all these different sums, you're going to get this as just okay. So here I'm just using the properties of the indicator here. That when you have that k squared times the indicator, that's just going to be xi squared because it's going to pick off the value that you find because you're doing this sum over the entire range. So again, if this step is confusing to you, that's something that you should just work through yourself to kind of make sure that that you can follow. And so when you complete this, you can rewrite this as so we get something very, very similar to what we had before. So we get by plug-in principle again. And recall that and so you can see that they're almost the same, but you do the n-1 correction for s squared. So the plug-in principle would just say you just take 1 over n, and the s squared does the n-1 correction. And the reason, if you recall, why we do this is to make sure that E of s squared is equal to sigma squared. Okay, so the upshot of this is that the plug-in principle kind of shows that gives us ways to calculate population parameters that are the mean and the variance. So if we return back to the Netflix example, so if we wanted to calculate the the net, if we wanted to look at the Netflix ratings for a movie, so remember that rating 1 had 270 people. Rating 2 had 140, rating 3 was 97, and then rating 4 was 228, and then rating 5 was 265, and that should hopefully all add up to 1,000. Therefore, the sample PMF okay, and so we want to find an estimate for the average overall rating. And a variance measure. Okay, and so this is where we can use the using the plug-in principle. Using the plug-in principle, and again, we've kind of learned these formulas a different way, but I'm illustrating the plug-in principle here. We know that mu hat is equal to x bar, and so using the we're going to illustrate this with the plug-in principle. Okay, and so this is just going to be and so if we go through that that calculation, we get this is 1 times So this is something that you can check and see if my calculation is correct. And hopefully you get, this kind of average rating of 3.078, which suggests that, you get you're kind of sort of like, and it's kind of an average movie, but remember that this is skewed because there's a lot who voted 1 and a lot who voted 4 and 5. So, if you looked at something different like the median, it would be something a lot higher than this kind of average rating. Okay, and you can also check that mu hat here is equal to x bar. So that's something you can check. So I've done this calculation specifically using the sample PMF so that we're using the plug-in principle. Now, if we find sigma hat squared using the plug-in principle, this just says that we use the formula so this is the plug-in. Okay, and so once again, this is a simple calculation to carry out, or hopefully something that you can do on your calculator, and so this gives you. So I'm not going to write it out, but when I went through this calculation, this is something you can check. What I ended up with was. So this is something you can check. So you have quite a high variance there. So even though you got this mean of 3.078, the variance was quite high, or the estimated variance, and that in some ways makes sense because this distribution is highly skewed to the both ends, and so that's why you get quite a high variability in the ratings. And another thing you can check is that. So you could certainly do the calculation in a different way and see if you get exactly the same thing. And that should certainly be true. Okay, so. So the plug-in principle is useful because it allows you to find approach to find. Let me just rewrite this. So it allows you to find estimator. Estimated for theta, which we'll call theta hat. That is any function of px of k. And the general idea is that if theta equals h of px of k, then theta hat, you just plug that in wherever you saw px of k, you just plug in p hat x of k. Okay, and we saw that with both the expectation and variance. Okay, and so So this provides a pretty general procedure for estimating theta. And so the next estimate, which is the method of moments, this is going to be kind of the first really key estimator that we're going to focus on, builds on the plug-in principle. It builds on the plug-in principle. So what does the method of moments estimator mean? So what it means is if we let mu equal to the expectation of x, and then we if theta is equal to some function of mu, then the method of moments works the following way, and it's called moments because it's related to the mean, which is the first moment of the random variable. So if your data here is x1, x2, up to xn, then we know that mu hat equal to mu hat is equal to 1 over n times the summation of xi. And so this equals to x bar. And so what you then say is that theta hat is equal to g of mu hat. And so plug in mu hat wherever you see. And so this is very useful because it's a function of mean mu. You can use method of moments to estimate theta. And so let's now illustrate this with an example. So let's assume that we have n random variables that are all drawn from an exponential lambda distribution. So clearly we know that, we know that again, it's very important to keep track of what are population quantities and what are sample quantities. So we know that mu, so we're working in the population right now. This is equal to 1 over lambda. So our goal here is to find an estimate for lambda, and we're going to use the method of moments procedure. So mu equals e of x, which is 1 over lambda, and so we know that mu hat equals to x bar, and then we know that lambda is equal to 1 over mu. So this is inverting mu equals 1 over lambda. And so therefore an estimate for lambda hat is just 1 over x bar. So here your lambda is equal to g of mu, which is 1 over mu. Therefore, lambda hat is equal to g of mu hat, which is 1 over x bar. Okay, so it's again following this idea of plugging into to what we know about the population to work out a quantity, to work out an estimate based on the sample. So the general procedure can be thought of as follows. For population distribution, determine mu as a function of theta. And so all that means is just calculate expectation. Okay, and so we'll say mu is equal to h of theta. Invert relationship. So this is how do you invert functions, and that's pretty straightforward, hopefully. So again, or this is something that you hopefully remember to some degree from your simple like analysis course, which is how to invert functions. Theta is going to be h inverse of mu, which is our g of mu, and then the estimate that you get is simply use a plug-in estimate mu hat for mu. So therefore we have that our estimate is theta hat, which is g of mu hat. Okay, so those are kind of the three steps that you need to follow from a calculations point of view to use the to use the idea of method of moments. Okay, and so we're going to do a number of examples here. So we're going to start with a simple kind of example that we've already seen. So if x1 through to xn is a Poisson lambda random variable, and we want to develop an estimator for lambda, which we'll call lambda hat, then we know that for step 1, mu, which equals to e of xi, is equal to lambda for a Poisson random variable. So it's again something that you can either look up in a table or calculate it. So therefore, mu equals lambda, and your h is just the identity function. It's very simple. The inverse of an identity is very simple to calculate. You just get that lambda equals mu. So your h is just the identity, your g, here is just the identity, and therefore you just get that lambda hat is equal to x bar, which we've already determined a number of different ways. And then the example we just saw before, I'll go through it again just to kind of put it into the framework that we've just seen. If we look at the exponential lambda random variable, for step 1, mu, which equals to e of xi, is 1 over lambda. So therefore we have that mu equals h of lambda is 1 over lambda. So you can think of it as h of x is 1 over x. And then we want to invert that relationship, which conveniently works out to just be exactly the same thing. So lambda is equal to 1 of mu, so your g of y is 1 over y here. And if you don't quite remember how to invert functions, the way to invert them is to just replace x and y, and then just do some algebra to get y on the one side. So I'll go through it explicitly here. So if we want to invert h of x, which is equal to 1 over x, the way to do that, if it's not something that you've you do, so we have that typically this, you can write this as y equals 1 over x. So now let's swap it around. So x equals 1 over y, and our goal is to get y by itself again. So therefore we have xy equals 1 and y equals 1 over x. So you kind of get back to exactly what you started with, which means that therefore we have that g of y is 1 over y. Okay, and so so that's just showing you how to invert functions, and therefore we have that lambda hat is equal to 1 over mu hat, which is 1 over x bar by plug-in, or by method of moments. Okay, so now let's do a couple more examples. So now let's look at x1 through to xn is distributed uniform 0 theta, and we have the additional constraint that theta is bigger than 0 to make this kind of a valid PDF. So so mu equals e of xi. So you can either look this up, or we can see how the integral looks. So the integral of uniform, so that's just going to be x times fx of x, because it's a continuous random variable over the range. So the range here, because it's uniform 0 theta, is 0 theta, and the PDF is just 1 over theta. And so we get that this is okay, and so this is just theta over 2, which is just the midpoint, which makes intuitive sense. So therefore we get that mu equals theta over 2. So your h of x is x over 2. Now we invert. So we invert. And you can hopefully see pretty easily that theta equals 2 mu. So your g of y is 2y, again, just by inverting that expression. And so therefore, so you can see that the first two steps have nothing to do with the sample data. It's only to do with the population parameters and the population PMF or PDF. But then the third step is where we incorporate the data. So that the theta hat equals 2 mu hat, which is 2x bar. So this is how we'd estimate it. And so the intuition behind this is that x bar, which is a sample average, is a good estimate of the midpoint for the uniform distribution. And so here what we have is is like to get the endpoint, which is the theta, we use 2x bar. Let's do another example just to get very comfortable with this. Let's look at the geometric distribution. So remember that the geometric is the so we covered it in the second lecture when we went through distributions. That's going to be 1 minus p to the k times p. And our goal is to find and so remember that the geometric distribution was just counting the number of failures that you had before the first success. So step one is to find the relation, to find the mean. So mu is equal to e of xi. And once again, this is something you can either look up or calculate, and you can see that that's 1 minus p over p. Okay, and I'm going to write it in a form that's a little bit more tractable, I think, which is that this is equal to 1 over p minus 1. And you'll see why we do this for inversion purposes. So you have that mu equals 1 over p minus 1. So your h of x here is 1 over x minus 1. We want to invert this expression. So we find p in terms of mu. So yeah, there's a number of ways you can do it. I would typically do it by just trying to put p on one side here. So let's do that. You can see that 1 over p equals mu plus 1, and then you can see that p equals 1 over mu plus 1. Okay, so this is what our g of y here is 1 over y plus 1. So by the method of moments, we just plug in mu hat wherever we see mu, so that then we get p hat is equal to 1 over mu hat plus 1, which equals 1 over x bar plus 1. Okay, so okay, so once again, what we have here is the population and then the sample. Then we have this relationship between mu and theta. And then in the sample, we have mu hat, which is just our x bar, which is our sample average. And then we have our theta hat. And so whatever the relationship is, so the way we've kind of defined it in the framework here is that theta equals to g of mu, and the inverse relationship is h. So we have that g equals h inverse or h equals g inverse. Then you get exactly the same relationships here. So we have that theta hat here equals g of mu hat. Okay, so what have we learned in this for the So in the terms of the statistical framework, we have our, I'm going to use the term sample data, x1, x2 up to xn. We have the this is the PDF or PMF indexed by some unknown parameter theta. Okay, so the population parameter here is theta. And what we've basically spent the last 20-30 minutes talking about is the estimator or the procedure. To find theta hat, which is the method of moments procedure. Okay. So the last kind of, in the context of our general framework, the last kind of 20-30 minutes is really focused on this question of this third step of finding an estimator for a general theta. So and we've kind of been through that basic idea of using the relationship between theta and the PMF or PDF or the mean in the population and translating that over to the sample. Okay, so let me just. Okay, so what we kind of haven't done yet, and what we'll talk a little bit about in the next lecture, although it's a little bit hard to generalize, is that the distribution of theta hat. So in particular, like if we want to do, is there some way we can get an asymptotic distribution of theta hat? So is there some way we can get an asymptotic distribution for theta hat? And I'm going to now use the notation here. Okay, so I'm going to just introduce some more notation here, which is the idea here is that there's many different kinds of estimators we can see. So far we've really just seen things like the sample mean and the sample variance. But in this lecture, we've seen a whole bunch of new estimators that are different. Are different because the method of moments sort of applies to any general parameter. And in the next couple of lectures, we're going to see another estimating procedure, which is the maximum likelihood. So this notation theta hat mm refers to the method of moments procedure, or I'll say the method of moments estimator for theta. And we're going to see the relevance of this in the next couple of lectures because we're going to introduce another estimating procedure, which is maximum likelihood. And so I want to distinguish between those two estimating procedures. So far, we've seen, estimators, like we haven't really used the subscript yet because we've there's really only been kind of one standard estimating procedure that we've used. But as we've seen, we've actually already seen two different estimates for the sample variance, which is the one with the n minus one and the one with just the one over n, and so those are different, even though they're pretty similar apart from a different factor. But we're going to see that you're going to get potentially very different estimators, and you need to somehow distinguish between them. So that subscript refers to the fact that you're using the method of moments procedure. Okay, and so that'll be sort of the main concepts that'll be covered in this lecture. And so in the next lecture, we're going to focus on trying to say a little bit more about the method of moments procedure. And then if we get time, we're going to move into kind of our next estimating procedure, which we're going to spend a bit of time on because it's quite widely used, which is the maximum likelihood procedure. Okay, thanks very much. Have a good rest of your day.